Okay, so we'll see memory interfacing. Now, to study the memory interfacing, first we need to know what is the memory. Okay, then we should know what is memory organization, and then we need to see how memory is interfaced to the ports of microcontroller. So we need to know the microcontroller ports to which the memory will get interfaced. Okay. Now, during the programming, we have seen that there are two types of memories which is inbuilt in the microprocessor. These are data memory and program memory. Okay. So these are on-chip memories which are available with the microcontroller. Now, if we want to expand this data memory or to the program memory, we can expand it by interfacing the memory to the microcontroller. Now, while interfacing the memory, we can treat that particular memory as a data memory. Okay. So we can interface external data memory. Okay. Similarly, we can interface the external program memory. External program memory. So here we are doing that depending upon the requirement, we can make the external memory as data memory, or we can treat it as the program memory. So it depends upon the configuration, how we are interfacing that memory to the microcontroller. Now, basically, when we see the memory here, the memory is represented in terms of the lines, in terms of the capacity and the word size. So for every memory, it has some sort of capacity and some sort of word size. Now, this capacity is defined by the number of lines which are needed to interface a specific memory. Okay. Now, for example, if suppose we have a single line, so using this single line, here a single either 0 or 1 data that can be transferred or that can be stored. Okay. So here the memory will be of 2 bytes. Now, if we have 2, then here from 0, 0, 0, 1, 1, 0, and 1, 1, that means here 4 bytes we can, 4 bits we can store in that specific location. If we have 3, then here the size will become 8. Then 4, that means here it becomes 16. So if the size is 5, it will become 32. That means here, depending upon the number of lines which are interfaced to a specific memory, here the capacity of that memory will get defined. Okay. And this capacity is represented in terms of equation as 2 raised to x, where x is the number of lines which are interfaced to the memory. And these lines are address lines. Okay. That means here, for a single bit, we can represent it by either 0 or 1. If we have two lines, we are representing the address of the two lines are 0, 0, 0, 1, 1, 0, and 1, 1. Similarly, if we have three lines, then 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. Okay. So according to the number of lines here, the capacity of memory is decided. So it is represented by 2 raised to x. Now, if suppose, if we consider the microcontroller, here we have 16 address lines. So for port 0 and for port 2. So the combination of these two makes 16 lines. That means 2 raised to 16, it gives about 64K memory, which we can interface to the microcontroller. Okay. Similarly, the second thing is the word size. Okay. So word size is nothing but on each line or each space, how many bits are stored. That means either we can store 2 bits, can be stored 4 bits, can be stored 8 bits. So it depends upon that. Here the word size is defined. Okay. So we'll take one example. If suppose I have 2 books or 2 notebooks. So here these 2 notebooks I can interface in such a way that the number of pages that will get increased. So if I interface these 2 books in such a way that the number of pages are increased. Let's assume here we have 100 pages, here we have 100 pages, and if I bind these two books together, then the total number of pages becomes 200. So total number of pages becomes 200. So here what I am doing, I am increasing the number of pages. So this increase in number of pages is called as increasing the capacity of book, okay, or capacity of memory. Okay. Now, if I interface these, or if I uh, bind these two books, like, the total number of pages will remains the same, but the size on each page will be increased. Okay, that means here the total size of this book will be like this. Okay, that will be the total size. So here the number of pages remains constant 100, but if suppose this page, single page is having 24 lines or 25 lines, then the number of lines on each page becomes, here the number of lines becomes 50. Okay. So here what happens? Here the word size of each page goes on increasing. So here total size remains constant. Okay, but here what happens? Here the size goes on increasing. Okay, so this increase in size is called as word size. Okay. So depending upon this capacity and memory, the equation can be represented as 2 raised to x by y. This is the capacity of memory. So where x represents the address line and y represents the word size. So here the number of lines which are available for x, okay, it is nothing but the address lines. Okay, and word size y, it depends upon the data lines. So it is called as word size, and it depends upon the data lines which are interfaced to the particular memory. Okay. Am I audible to everyone? Am I audible? Is there any problem with joining? Vinod, it is auto joining. Just ask Darshan again to retry for joining. इथून काही प्रॉब्लेम नाहीये रे, कारण इथून तरी मी डायरेक्ट ऑटो जॉईन आहे, सगळे जॉईन होत आहेत. झाला का दर्शन जॉईन? ओके, नाउ इफ यू हॅव एनी क्युरीज, जर कोणाला काही शंका असतील किंवा काही समजलं नसेल तर डायरेक्टली मला माईक टर्न ऑन करून जस्ट क्युरी विचारा, कारण मी चॅट विंडो बघू शकत नाहीये. आय एम प्रेझेंटिंग द प्रेझेंटेशन. ओके, पॉवर पॉईंट मी काढतोय, त्यामुळे मला तुमचे चॅटिंग काहीही दिसत नाहीयेत. सो जर काही क्युरी असेल तर तुम्ही डायरेक्टली माईक टर्न ऑन करून मला क्युरी विचारा. ठीक आहे? हा प्रियांका, पूनमचा काय प्रॉब्लेम? जॉईन होत नाहीये का?
हो सर.
ओके, तिला जॉईन करायला सांग 2-3 वेळा ट्राय करून, कारण ऑटो जॉईनिंग असल्यामुळं मला तर काहीतरी अलाव करण्याचा वगैरे काही संबंधच येत नाही, डायरेक्टली होऊन जाईल ते. ठीक आहे? आणि जर काही क्युरी असेल माईक टर्न ऑन करून क्युरी विचारा. ठीक आहे? ओके, सो आपण कुठे होतो? हा, सो एक्स is representing the address line and y is representing the word size or data lines of which are interfaced to that particular memory. Okay. Now we take the example. If suppose we have the memory, we have address lines. Okay. If suppose we have 4 address lines and 4 data lines, then the capacity of memory that we can interface using 4 address lines and 4 data lines are 2 raised to 4 multiplied by 4. So it is 16 by 4. It is the memory capacity or the memory which we can interface to the particular processor or device. Okay. Now, if we have 5 or we'll take the example of 10 address lines and 8 data lines, then we can interface 2 raised to 10 multiplied by 8. So it is equal to, I think, around 1K by 4. Sorry, 1K by 4. So this is the memory capacity. Okay. So for the sake of simplicity, what I will do, we will draw a table where we can represent the address line and the capacity. Okay. So here, if we have one address line, then here we can, the capacity will be 2 bit. We have 2 address lines, then it is 4. If we have 3, then 8. 4, then 16. 5, 32. 6, 64. 7, 128. 8, 256. 9, 512. 10, 1024. So this 1024, it is represented by 1K. So if we have 11, then it is 2K. If we have 12 lines, then the capacity is 4K. If we have 13 lines, then 8K. 14 lines, then 16K. 15 lines, then 32K. And 16 lines, then 64K. So according to the number of address lines here, the capacity of memory goes on varying. So if you have been asked to identify the number of address lines required to interface 2K memory or 2K by 8 memory, so what does it mean? Here for this 2K, how many address lines are required? 11 address lines. So here the address lines will be 11 and data lines will be 8. So these are 8 data lines. So these much of address and data lines are required to interface 2K by 8 memory. Okay, everyone understood it? Now, before going to the memory organization, first we need to know what is the types or what are the different types of memories. Okay. Now, here for different types of memory, here the memory can be separated, or this memory is divided into 2 types. One will be the read-only memory and one will be the random access memory. Okay. So what is the meaning of read-only memory? Here, this memory is written for a single time. Okay. And this will not what we can say, the flash the data, or it will not lose the data if suppose any power fluctuation occurs, or due to if we turn off the memory or if we turn off the system. So in that case, here this data will not get lost. Okay. So here we can read the data, but we cannot write the data. So we can read the data here, and for writing the data or data operation into the memory, that cannot be possible in read-only memory. But for RAM, here it is random access memory. That means here the programmer or the user can read the data which is available into the memory, at the same time also can write the data into the memory. Okay. So reading and writing is available into the random access memory, and in the read only memory, here only we can read the memory, not write the memory. Okay. Now here this ROM is again have different types. Okay, in which first one is PROM, that is programmable read only memory. Then second is EPROM, that is erasable programmable read only memory. And third one is EEPROM. Okay. Now here this programmable read only memory, it is also called as ROM. So here if the memory is programmed first, okay, then after programming, here it has the fuses. So according to the programming, or according to the data, here these fuses are flashed. Okay, and it will blow some sort of fuses. So if the fuse is connected, that will be 1. If the fuse is disconnected, that will be 0. So 1 0 1 0, so on, like that the data will get stored. And once the data is stored, here that data cannot be changed into the programmable read-only memory. Okay. Now in EPROM, here it is called as erasable programmable read-only memory. So here whatever the memory is available, that memory can be erased and again programmed by using ultraviolet light. Okay. So for this memory, it has one window on the memory where the ultraviolet light is exposed. Okay. And when the light is exposed on this memory, here all the data which is available into the memory, that is getting erased, and again that will get programmed. Okay. But the time required for erasing this memory or EPROM is about more than 20 minutes. So that much of time is required to erase this EPROM. Okay. So here one more programmable read-only memory is available, that is called as EEPROM. It is called as electrically erasable. Electrically erasable programmable read-only memory. So here, what happens, in spite of exposing the memory to the ultraviolet light, here this memory can be electrically erased by providing the power supply to that particular memory, and again that will get reprogrammed. So here this is the EPROM which will get electrically erasable. That's why it is called as EEPROM. Okay. Similarly, again, we have different memories like flash, ROM, or mask ROM, and so on. Okay. Now, in the RAM, here this RAM is also divided into different types, in which the first one is SRAM. So it is called as static RAM. Okay. So it is made up of a flip-flop. So according to the change in status of flip-flop or change in clock of flip-flop, here the data will get changed. So here the storage of the data is nothing but the flip-flops in which the data is getting stored. Okay. So that data can be read or can be write also. Okay. The second is NVRAM. It is called as non-volatile RAM. Okay. So it is just like a static RAM, okay, but the difference is here uh, for this NVROM, it has a control circuitry, and using that control circuitry and transistorized configuration of this RAM, it makes it as NVRAM. So here also we can read the data as well as we can write the data. Okay. And one more RAM is available here, that is called as DRAM, that is dynamic RAM. Okay. So here also it is nothing but the configuration of flip-flops, and but it is different as compared compared to the static RAM, because here here what is static RAM, it is flip flops, and for dynamic RAM here the capacitors are used to store the data. Okay, so working of same as that of flip flops, or working is same as that of static RAM, but here the capacitors are used as the what we can say, memory storage locations. Okay, so these are the different types of memories which we can interface to the microcontroller. Now we will move towards the organization of memory. So here we will see memory organization. Now, what does it mean? So when we are using or we are interfacing the memory to a specific processor or controller, we need to identify how many address lines and data lines are required for interfacing of that memory. Okay. So here we can do that by using the combination of address and data lines. Okay. So here what we'll do, we will take the example of two memories. Before that, what we'll do, we will take one example, and with the example we will check how the memory is organized into the or interface to the microcontroller. Okay. Now let's assume we have the capacity which we can interface to the microcontroller is 2K by 8. That is the capacity, and we have available memory it is 1K by 8. Okay, so this is the available memory. Now using 1K by 8 memory, we need to make the capacity of the external memory which we need to interface to the microcontroller should be 2K. So here if we observe it, we can identify that we need to increase the capacity, not the word size. So here the word size is same, here also required also and available also. Okay. So the number of chips required for interfacing is identified by the equation number of chips is equal to required memory to the available memory. Now here, what is the required memory? It is 2K by 8. And what is the available memory? It is 1K by 8. So how many chips are required? So 2 chips are required to interface 2K by 8 memory to the microcontroller using 1K by 8. Okay. Now, the same, we will take one more example here. If suppose required memory is 1K by 8 and available memory is 1K by 4, then the number of chips which we need to interface to the microcontroller is given by required memory to the available memory. Now, if we observe these two, here the capacity is remaining constant, but the word size will go on increasing. So here it will be 1K by 8 with the available 1K by 4. So here the number of chips required are 2. So either we increase the word size or we need to increase the capacity. Here the number of chips required for interfacing will go on increasing. Okay, so here we are increasing the word size of each page. Okay. Now we will see how we organize it. Now, what was the previous example? We have 2K by 8. We require 2K by 8 with the available memory of 1K by 8. So here, this is, let's assume this is the first memory with 1K by 8. Okay. And this is the another memory. I will draw here. This is the another memory of 1K by 8. So for 1K, how many address lines are required? If we see the previous year, for 1K, how many address lines are required? 10 address lines. Now, if we see the address lines, these address lines starts from A0. So these 16 address lines are written as A0 to A15. That means 10 lines are represented by A0 to A9. A stands for address lines. Okay. So for 10 address lines, the range is A0 to A10. That means 10 address lines are required here. So I will write here as A0 to A9. Now for 2K, what we need to interface 2K. Okay. So in this previous session here, what I have told you. So here, depending upon the address line, the capacity of that particular memory which we are going to interface is decided. Now, what is the required capacity of memory which we need to interface? It is 2K. And for 2K, how many address lines are required? 11 address lines. Okay. And here what we are doing, we are interfacing only 10 address lines to A0 to A9. Okay. Now these lines will be common for both the memory chips. Because here we are increasing the number of pages. Okay. So here the word size will not get increased, or the number of lines on each page will not go on increasing, but the number of pages in that book will go on increasing. So here this A0 to A9 will be common for these two lines. Okay. Now the data lines, as it has the word size of 8, the data lines will be D0 to D7. So hello, what is the problem? So this D0 to D7, these lines are also common for both the memory chips. Okay, because here the word size is 8 for required memory also and for available memory also. Okay. So here these lines will remain common. Now one more line is available, that is A11. No, sorry, A10. That is 11th line. Now this line also we need to interface to this memory. Okay. And this interfacing or this line will be used for chip selection like this. So it is called as CS bar. So this A10 line, directly it is interfaced to the first chip as it is, and by inverting that line, it will interface to the second memory for chip selection. Now, why it is done so? So here, if suppose I'm binding these two bits so that the number of pages goes on increasing, and if I want to read the data from first book, I need not require to open the second book. Okay, so directly I can open the first book and I can read the data. Okay. So if the first book is having 100 pages, second book is having 100 pages, and if I am binding together, it makes 200 pages, right? Now, if I want to read the data from 55 memory of 55th page, so if I want to open this 55th page, I need not require to open the book or the pages more than 100. That means from 101 onwards, I need not require to open. So if I only need to open the first book. Okay. So that will get enabled by this chip selection. Similarly, if I want to read the data from 160th page, so in that case, I need not require to open the first book. Okay. So here the second memory will get accessed or enabled by this chip selection. So CS bar, it is called as chip selection bar. Already in the first lecture, during the starting of microcontroller session, I have explained to you the different devices which were need to interface to the microcontroller. So here we have seen the buffers, the latch, then we have seen the decoders and so on. So here the function of decoders and buffers and latches are come into the picture. So if this A10 line is 0, by default, first memory will get selected. And if this line, A10 line is 1, then after inverting, it is interfaced to the second memory chip. So second memory will get enabled. Okay. If so depending upon the status of this A10 pin, here either first memory or second memory will get enabled. Okay. Everyone understood it? सगळ्यांना लक्षात येतं का? हे इम्पॉर्टंट आहे मेमरी इंटरफेसिंग साठी. सो जर समजत नसेल तर विचारा. काही क्युरीज आहेत का? अरे बोला रे बाळानो.
नो सर.
सर्वांना समजलेलं आहे ना? अरे समजते का सर्वांना? Okay, so here we have seen the increasing the capacity of memory. Now, what we will do, we will move towards the next part, that if we need to interface in such a way that the word size will go on increasing. Okay. So here, the second example which we have taken, we want to interface 1K by 8 memory with the available memory chip of 1K by 4. So in that case also, we need to interface here 2 memory chips. So in this case here, let's assume this is the first 1K memory. This is the second 1K memory. So it is 1K by 4 and it is 1K by 8. Sorry, 1K by 4. Now here for 1K, how many address lines are required? A0 to A9. So this A0 to A9, that will be common for both the memory chips. A0 to A9. Now see here, like the previous example here, for 1K, how many address lines are required? 10 lines are required. Okay. Now required memory is also 1K. And available memory is also 1K. So we need not require to increase the capacity of memory, right? Only we need to increase the word size. Now here, if we see this example, here A0 to A9, these 10 lines, address lines, are common for first memory also and for second memory also. So capacity part is over. Now for data lines, here we are increasing the word size. That means from the page, this binding of two books is like that, where the number of lines on each page will go on increasing, or the size of each page will go on increasing. So for first 1K by 4, how many data lines are required? 4 data lines. So D0 to D3. These lines are required for first memory. Okay. Now remaining 4 lines are interfaced to the second memory, D4 to D7. So the combination of all these together make it as 8 data lines. So here the word size on each page will go on increasing if I make the combination in such a way that we need to increase the word size. Okay. Now see this difference here. When we are increasing the capacity of memory, here the address line will go on increasing. And in this case here, whatever the extra address lines are available, these address lines are used for chip selection. Okay. Now for increasing the word size, here by default the maximum word size which we can interface to the microcontroller is 8. Now if we have 4 data lines or four word size memory, and if we want to make it as 8 word size memory, then here separate D0 to D3 lines, or separate 4 lines are interfaced to the first memory and separate 4 lines are interfaced to the second memory, so that the combination of these together will increase the word size. Okay, everyone understood it? So this is the way of memory organization. Okay. Now we will move towards the memory addressing. So we will see how memory is addressed. Okay, or addressing. Now here, to understand the memory addressing, here first we need to understand how many address lines are available for microcontroller. Now for microcontroller, here we have address lines are 16 and data lines are 8. So that much of address and data lines are available to the memory. Now in the 16 address lines, here 8 address lines are available at port 0, and these are multiplexed address lines. Okay, that means the same lines are working as address as well as data. Okay. Similarly, the remaining 8 address lines are available to the port 2, and these are called as higher address line. Okay. So A0 to A8 are available to the port 0, and A9 to A15 are available to the port 2. Now these data lines are available at port 0 because it is multiplex address and data lines. Now, how this multiplexing is demultiplexed? Okay. I think in the first or second lecture, I have seen, I have explained to you how the multiplexing takes place. Okay. Multiplexing and demultiplexing. But still, we will take the example here. Okay. Now, let's assume I will draw microcontroller here. Pardon for the design. Okay. I will draw it properly. I will try to draw. So we will draw here the memory like this. Sorry, not memory, it is microcontroller. Okay. And in this microcontroller, we have multiplexed address data lines at port 0. And these are AD0 to AD7. Now, these lines are first connected to the latch 74LS373. So for this latch, this multiplex address data lines are connected. Okay. Now the output of these latch are nothing but the address lines A0 to A7. So it is A0 to A7. These are the separate address lines. These are interfaced to the memory as it is. So it will be A0 to A9. Again, before 74LS373, it is interfaced directly to the memory as a data lines. So it will be D0 to D7. This will work as data lines. And this latch is enabled by the ALE, address latch enabled. So when this is active high, or when the high pulse is provided to the 74LS373, so it works as a buffer. So whatever the input which is available at this input side, that will get switched to the output side, and it will notify the address. Okay. So it will access the address. Now, when microcontroller wants to read the data or to write the data, then when the read bar signal goes low, read bar and write bar, already we have seen these pins which are available into the pin configuration. Okay, so when this read bar signal goes low, at the time microcontroller is ready to read the data from memory. Okay. So that data will directly get accessed by the microcontroller through this way or through this channel. Okay. Now, if microcontroller wants to write the data, after first latch is enabled and data is shifted towards the address side, these lines are free for next data. So whatever the next data which microcontroller wants to write on the memory, that data is available to the port 0. Okay. And when write bar signal goes low, at that time, this data is written directly on the memory. Okay, so here using 74LS373 latch, here the address and data lines are separated. Demultiplexing means separation of address and data lines. Okay, so here when the ALE goes high, the input side is latched to the output side and it will be treated as address or the memory address. And when it is low or ALE is low, at the time whatever the data is available on these lines, that will be either read it by the microcontroller, or if microcontroller wants to write the data, it will send that data to the port and that will be written here. Okay, so using 74LS373, here the latch, here the address and data lines are separated or demultiplexed. Okay, now we will see the working of this latching and decoder during the actual interfacing of the memory. Okay, now we will see how the memory addressing is done. What is the problem? Okay, we will take one more page. Okay. Now, while identifying the memory addressing here, first we need to write the address lines like this: A0, A1, A2, A3, A4, A5, A6, A7, A8, 9, A10, A11, A12, A13, A14, and A15. Now, here if we want to identify the capacity, if suppose the first address is 0000, okay. So here the address is represented like this: 0000, 0000, 0000. This is the initial address of the memory. We will write it as 0000. Okay. Now, from this memory location, if suppose at 0100 that much of memory is specified for a specific operation or reserved, then it is represented as first 0 will be 0000, then next one will be 0000, next is 010 na, so it will be 10 1000 and then 0000. Okay, so here the transaction is from, so this much of space it is available here, or which is available here, that is reserved space. Okay, so this much of space is reserved for specific operation or for interfacing a specific memory. Okay, now if we want to interface 1K memory, that means here from the initial location, here how many lines are required for interfacing A0 to, from this to this A0 to A9. So that much of lines are required to interface the 1K memory. And how much space is reserved here? So here the transaction or the transition from all the pins from 0000 to 1111, 1111, 11. Okay, remaining will be 0 as it is. Okay. So A0 to A9, that this much of space is reserved by this 1K memory. So the status of A0 to A9, or for the sake of simplicity, if suppose we have two lines, how many memory locations are reserved? First will be 00, or address will be 00, then next address will be 01, then next address will be 10, next address will be 11. Okay, so if we have two lines, here the first address will be 00 and last address will be 11. So this much of address is reserved or interfaced by using two lines. So similarly, if we have 10 lines, here how much address will get reserved? So first 10 lines are 00000000 and 00. So from here, if we drop for every stages here, the address will become this 00, then this bit will become 1, then 10, then 11, so on. Up to how much of space? All the line becomes 1111. So this much of space is reserved by 10 lines, okay, or addressed by these 10 lines. So if we define the address, the first address will be 0000H and the last address will be F, then F, and then 3. So 03FF, that will be the highest address which we can point or which can be addressed by space of 1K memory. Okay, if we want to interface next memory, again after this address, the next address will become here 1, or this A11th, 8/10th. So this 8/10th bit becomes 1, then the remaining bits becomes 0000, 000000. Okay, so this will be the starting address of next memory of 1K. So this address will be 0400 onwards up to how much of space? 07FFH. So all the pins become 00002. The maximum status will be, or maximum address will be 1111, 1111, 111. So that will be the maximum space which is acquired by one more 1K memory. So here this is first 1K memory and this is second 1K memory. Okay, so like this, here the memory will get addressed in the memory addressing. Now see here, in the first case, if we interface 1K memory, the maximum status will be here. Now if we interface the next memory here, this A10 line becomes 1, all the line becomes 00 like here. And up to which what much of space? Here A10 line remaining 1 as it is, and remaining lines becomes 1111. So if I represent it like this, then the status of this A10 pin will be 0 for first memory and 1 for second memory. Okay. So here, depending upon this status or change of status from 0 to 1, here the memory can be pointed. So here, what happens if suppose the status of A10 pin is 0, then the data from first 1K memory or this address lines are pointing first 1K memory. Okay. So here the A10 line is remaining 0 for the address 00211. Okay. And the status of this A10 pin becomes 1 for second memory. That's why here when we are increasing the memory, here what happens? Here the status of this A10 pin is 0 for first memory. So first memory will get selected, and it becomes 1, then this, by inverting it, it is interfaced to the second memory, so second memory will get selected. Okay. So here, when we are reading the data, here, depending upon the status of this A10 lines, here the data will get accessed. Okay. That's why here this A10 line is used for chip selection. So if this A10 line is 0, first memory chip is getting selected. If this A10 line is 1, then second memory will get selected. So depending upon this, here the chip selection is done. Okay, everybody understood it? सगळ्यांना समजलं का?